Yeah, hi. I'm Timo Kersten from Technical University of Munich, and I present on the paper on another level how to debug compiling query engines. And this is joint work with Thomas Neumann. Actually, my paper kind of picks off where we just left. Once we found a bug and we know that there's a bug in there, then you can use the technique that I'm going to talk about. Well, in general, using code generation to execute queries is now a very popular approach. Hyper uses it, Spark uses it, MemSQL does it, and Peloton did use it too. Well, unfortunately, debugging generated code is quite hard. It is often complicated to trace back generated code into the handwritten code that did generate the code. So in this talk, I'll present a solution. I will present a multi-level debugger. It provides context for generated code, and it makes it much easier to trace back into the code generation. For our database project Umbra, it was already really helpful, and maybe, but this is just speculation, such a multi-level debugger could have saved the Peloton system from discontinuation, maybe. So I expect that not everyone is familiar with the details of relational engines that generate code. So I want to make this talk very concrete, and I will use a running example to illustrate the problem. I will also use this example in a short demo of the debugger. Here you can see the example query. There are two tables of movie ratings from different sources, Rotating Tomatoes and the movie database. And as a query, we ask, are there any movies which receive the same rating from both sources? Also, we only consider movies that received more than 10 ratings in the movie database. And the example problem is that our database system counts 0 matching tuples. But in reality, actually, in the data, there are some matching tuples. So now let's have a look at how to debug such a case. We see that the query plan is okay. So we suspect the bug to be somewhere in the execution engine. Query execution with code generation is split into two distinct phases. First, we generate the code for a query plan, and we call this phase compile time. And then we run the generated code and produce the query result. We refer to this as the runtime. Our example query also goes through this process. First, we generate the code for the query plan, and the creating code looks like this. So here there's a snippet from a hash join. It takes a tuple from the right-hand side and does a hash table lookup to find a join partner. And the code that is generated looks something like this. Now, to find a bug, we can attach a debugger to step through the code and see what happens. Option 1 would be to set a breakpoint in the code generation process. This code is handwritten, so we find comments, we find nicely named variables, we find modular code, and overall, the source code is nicely readable. Well, unfortunately, the bug doesn't really manifest here. After all, we only generate the code, but we don't work on the actual data. So option 2 is to set a breakpoint in the generated code, actually in the generated code. So the bug manifests here, but the question kind of is, hey, would we realize it when we see the bug? The generated code is rather low level, and most of the time we don't understand at first glance where all those instructions come from and why they are in there and which operator they belong to, and generally which function they are serving. So to address this problem, we propose to use a debugger which can debug runtime and compile time simultaneously. With this approach, we can run and debug the generated code at the same time, and also debug the code generation to better understand the running code. We propose to do a simultaneous debugging with the help of a time-traveling debugger. A time-traveling debugger goes beyond a regular debugger, like for example GDB. A time-traveling debugger can stop a program at one point and step execution forward, as you're familiar with, but it can also step execution backward, so we can go back in time. For our debugger, we use the RR debugger, which is an open source project from Mozilla. And RR creates a complete recording of a program run, and we can replay that recording for debugging. Now, to debug code generation, we can combine time traveling with unique identifiers that we have for every instruction that was generated for the code. The unique identifier lets us stop the debugger exactly where the instruction is generated. So that means while we run the generated code, so we execute the generated code and step through some of the instructions, we can also go back in time exactly to the moment where those instructions were generated. This may sound a little bit complicated, so I think it's time to run a demo to see, so that you can see what it is actually like. So here you see our database system Umbra, and maybe you recognize the example query already. And now that I run it, the result is result count 0, so we didn't find any match. That is unfortunate, sorry. What I actually wanted to do is this. We can see that there is, in the movie database, there's a tuple, and the other one didn't work. Great, you can already see it's a real demo. There's also a tuple, and there should actually be a match. Even the reviews are larger than 22, so actually it should work. Apparently there's a bug somewhere in our system, and let's go about debugging it. The first thing I'll do is I'll just use the query from a file, and I can see, well, I can run it, and now I can use RR to create a recording. This again ran the database system and created a recording of the query execution, and now I can ask RR to replay. Now it drops me into GDB, and I used this little prepared breakpoint, which I had from beforehand, just to make this a little shorter, and I'll continue to that so that we get dropped in the generated code. Here you can see some part of the generated code from our Umbra database system, and we're in the pipeline that actually does the hash table lookup. If we have a look at down here, a little more, we can see, well, there's some lookup in the hash table going on, and that's where we want to get to. Now, if we go back and say, okay, just go to the next instruction, we can step through this, and let's go down a little further and try to go to the hash table, to the actual lookup. Oh, well, that's unfortunate. We just jumped over the lookup. What happened here? We can use reverse next. That's one of the capabilities of a time traveling debugger, and see, well, the previous instruction was this conditional branch. If this code looks very confusing to you, that's good. That's what it's supposed to be doing, because most of the time when we look at this code, we can't really tell what it is for. For example, here's some floating point conversion to integer going on, and integer back to floating point, and there's this comparison, and we don't really know what these instructions mean and where they come from. So what we can do now is go to the second level and use our time traveling capabilities to go to the point where this instruction was generated. So I'll say this is our extension to GDB, this go to instruction command. I'll say go to instruction 5038, and it'll happily drop me here, actually in the hash table probe. Now if we go down the call stack, we will see now we're in the hash table, and it's doing some probing thing, and exactly where this if is, that's where the conditional branch here is generated. And apparently it checks an outside domain indicator. Well, now, assuming I'm here for the first time debugging this, I'm not sure what this outside domain indicator is, because most likely somebody else wrote the code. So what I can do is I can follow up on the outside domain indicator, and in the generated code, I can see that the input for the conditional branch actually comes from the comparison directly before this. So I can just say, please show me this other instruction, 5024, where did that come from? And if I look up, I see, okay, I'm still in the hash table probe, and I can go down to collect probe key. That is something where we collect all the keys for the hash table lookup. And now I can do something interesting. While running the actual, while actually debugging the code, debugging the running code, I can go back and debug the code generation, and I can even go back in the code generation and say, hey, print some variables from here. And here I can say, okay, during the code generation, this compare types was varchar and integer. This isn't super helpful at this point, so let's go down the call stack and see what actually happens in collect probe key. There's some casting for equality going on, and then we're apparently routing to the correct cast. And here we arrive at the correct cast. I don't want to go into the details of what's happening here, but just let me tell you that we're casting a double here to an integer, and we're also checking for a violation, and that happens when we're casting a double to an integer and there's some information loss. That means we're not casting to an exact integer, or in case we can't cast back to that double, we get this violation. Okay, but wait, where the conditional branch was at instruction 5038. Let's go actually down to this branch. Let me clear that. Here it says, if we're outside the domain, then do the probe logic. So if we can't find a join partner, then do the hash table probe logic. Well, that seems wrong. And now we can use this information and go back to the source code and fix this here. And we can say, well, if we're not outside the domain, then do the probe logic. Let's check if our fix actually worked. Rebuild the project, and then I'll just rerun it. No need to record again. All right, and we found a match. Great. So I hope you could see that it's very convenient to be able to debug runtime and compile time simultaneously. Another interesting aspect of this debugger and this debugging approach is that it's actually relatively easy to implement. As I've shown you, we used RR for recording. And then in the replay, we used a conditional breakpoint similar to the one that I'm showing here on the slide. And we use it to stop exactly where the instruction is generated. This kind of conditional breakpoint constitutes the core of the multi-level debugger. We also add some other tools to make navigation quicker and to integrate with external processes. But overall, our extensions to GDB are only about 70 lines of Python. I would say it should be relatively easy to implement our debugging approach for other database systems as well. So now you may think, well, this sounds great. So what's the catch? Well, since we're using a time travel debugger, we must record the whole execution. And this obviously introduces some overhead. So to give you an idea, RR can record the execution of TPCH scale factor 1, query 1. And for this, it creates almost 500 megabytes of recorded data. And the runtime rises from 1 second to 10 seconds. This is a slowdown, but I must say I still find it impressive. After all, RR creates a complete and also deterministic recording of everything that happens in the process and gives us the ability to move forward and also backward. Anyway, in case the overhead of recording everything in the process becomes too large, we could also use a fallback. For example, as a fallback, we can only record the code generation process and execute the rest with the regular debugger. Overall, this makes our multi-level debugger ready for a really wide range of cases. The multi-level debugger reconnects generated code with the code generator. So one advantage is that it helps expert developers to find bugs quicker, but I also believe that it's a great tool for everyone who wants to get started in a project that already uses code generation. Yeah, this concludes my talk. I hope you now really want to try this debugging technique on your favorite system. Are there any questions?
Thanks a lot, Timo, for the great presentation. So any questions? We still have plenty of time. So I mean, maybe to quickly kick it off, Timo, so you mentioned the performance hit or the overhead of basically using the reverse debugger. Did you also encounter other limitations like with multi-threading or similar things that might be difficult for a database system, or is it generally applicable?
Yeah, that, for example, we used RR, and RR is a good product and you can use it to debug lots of things, but it happens that you run into cases where RR just needs to give up, or when you're in the replay, you encounter a bug in RR actually. And I would say it's production ready to a degree, but once the recording becomes large, for example, then you have to think of other ways to handle it. Ah, this looks better.
Hey, I'd ask a question. So it's really kind of cool using the time traveling debugger to, correlate things that happen at different times. You're taking advantage of the fact that the code is that something is compiled down to code. But could you apply? There's other cases where things aren't compiled down to code, but you have one thing that's scheduled. Schedule's made over here. It's executed over here. Could this kind of thing be used for that also?
Yeah, I guess it can, as long as you can link it back together somehow. In my demo, I used this, that we know exactly at which point or at which instruction we are, and then go back in time to search for the point where this instruction was generated. When you say, I want to do the same thing, I'm running a specific task, say task 53, and I want to go back to the point when task 53 was actually enqueued, sure, you can also do that.
Yeah, that could be really cool. Thank you.
Thank you.